I'm very excited to introduce to you our next speaker. I know we have about 45 minutes of hearing some of the great wisdom from this man here. Many of you I know have heard from him and have seen some of the work he's put out. I know we had some folks coming up getting some book signings right before we just got started. You may have seen some of his work on machine learning on GCP or data science on GCP. He's very vocal on Medium and really a great source of wisdom in the industry. He spoke yesterday at Next on TensorFlow, and today, obviously, the CPUs, GPUs. Now we're getting into TPUs. So before he came over to Google, he did some work with NOAA, which has been great because we've had a lot of Kaggle competitions with NOAA as well. So, but with that, again, very excited. I'm going to give a round of applause for Lak.
Yeah, thanks, Addison. It's great to be here at Kaggle. I remember running a couple of Kaggle competitions, once when I was at NOAA, and another time when I was at Climate, and we basically did a Kaggle competition around predicting rainfall. But this was just before the deep learning, the craze took off, and I've always wondered what would happen if we went back and we basically, instead of, we were just providing individual structured points, and it was like, what would happen if we now provided snippets of radar images, and I think we could actually do a whole lot better. But what I want to talk about today is about how to do accelerated data science, right? So we're going to basically talk about how to train, in particular, image and text models. And I'll talk about why it is that I didn't just say training machine learning models, but specifically I talk about image models and text models, how to do them faster using TPUs. So we'll basically talk about why we're going to be talking about TPUs, why did Google develop TPUs, and a little bit about how TPUs work. So I've always done software. My background is electrical engineering, but I've never actually built devices. And so the last year or so, I've gotten to kind of work more closely with the TPU team. And it's kind of cool to be in a group where there's a whole bunch of jargon you don't quite understand, all these hardware jargon. And over time, I've been picking those things up. And it's very, very, very cool. So I'll kind of hope to get some of that thing into you. How TPUs work, why are they fast? Because that also helps you understand where you get the speed ups. And it basically also explains my title of why I'm basically focusing on image models and text models and not just any ML models. Then I'll talk about how to develop with TPUs. So I've given this talk maybe about 7-8 months ago when we were just getting started with TPU version 2, and that developing with TPUs was about 15 slides of extremely dense information, but this is all the stuff that you have to do. Turns out now, developing with TPUs, use Keras, right? Mostly it works, but it also comes back to the things that we'll talk about in the first place. TPUs are going to be fast in certain situations, and we have to basically account for those situations when we do our Keras models. Then I'll basically look at state-of-the-art image models, things like ResNet, for example. How do you basically take them and how do you run them? And I'll talk about state-of-the-art text models and how do you take them and how do you run them. And in both of these cases, I'm going to be talking about models that have already been adapted to run on the TPU. Okay? So the idea is that if you have a model that basically does image classification or that needs to do text classification, instead of starting from scratch, you're often better off starting from a really good starting point. And I'm basically going to talk about those two starting points there. And finally, right, we'll basically do a quick hands-on where you get a choice of developing your own model, that's developing the TPUs, or of trying out an image model or trying out a text model, right? So you basically have your choice of doing any of those three things. So the first bit is, why on earth do we care about TPUs, and why is it that we want to do this? And the graph on the left, and those of you who were in my talk yesterday probably saw this graph, so forgive me, but I'll go through it slower. It's basically looking at how the error rate decreases as your data size grows. Now, this is a specific kind of model. This is a text translation model. So the x-axis here is the number of words that you need to train a good translation model. But the same kind of thing works regardless of the type of data that you're dealing with. Okay, the same kind of behavior is there. So if you look on the y-axis, It's basically the error rate, and it's 0.67, 0.62, etc. It's pretty linear. But look at the x-axis. Right? The x-axis is 2 power 20, 2 power 21, 2 power 22. What's happening on the x-axis? What's happening at to go from one grid line to the next grid line? The data set is doubling, right? So to get a linear reduction in error, you basically need double the size of data. Now, if you're in a Kaggle competition, they give you the data beforehand, you really don't have a chance to go out and double the data. But in the real world, right, when you're building an enterprise system, you often have to make this choice. Do I spend my time building a better model, or do I spend my time going and figuring out how to get more data? And that is what the two lines are. The blue line is a model with 200 hidden nodes, and the red line is a model with 512 hidden nodes. So approximately a model that's twice as deep. And what happens, like look at the left-hand side of the curve. What happens, right, if you basically get a better model? How much improvement in error rate happens versus what happens if you double the data? Can you guys see that? Which is more? The impact due to doubling of the data size or the impact due to a better model? I'll basically summarize this for you. And it's essentially that the amount of improvement that you get by doubling the data is much, much, much more than the amount of improvement you get from a better model. But then once you go to the right-hand side, you have a lot of data. And at that point, you start to see that the graphs are kind of diverging. Do you see that? And then when you're doubling the data, it's not going to have that much of an impact, and a deeper model starts to have more of an impact. Are you all seeing this, right? So part of being part of an enterprise data science team is kind of recognizing where in this regime you are. Are you in the regime where you need more data, or are you in the regime where you need more sophisticated models? And most commonly, you are on the left-hand side, and you want to go collect more data. So that's one reason why ML models keep on getting better, is because data sizes keep growing. The second aspect of this is what the second graph is showing. This is the years, and these are the compute requirements by year. And you basically see out here is AlexNet, which is basically what started the deep learning revolution. And out here is AutoML, neural architecture search. And the difference in compute here is about 10,000 times. Okay? So if the kind of things that we would do a few years ago, right, that you would do on one GPU, are the kinds of things that we would need 10,000 GPUs for now, because the models are more deep and sophisticated. So take those two things together, and that's the thing that's driving a lot of the stuff that's going on at Google. The other bit is the fact that pretty much any enterprise model is going to require about 5 to 100 million weights that you need to adjust. So 95% of the models that we use in production at Google are between 5 and 100 million weights. So these are very big models. And as you know, training a model that requires that much data is going to take quite a bit of time. Right? It's very, very, very difficult to train, but it's also it's going to be very expensive when it comes to prediction too, because you have to carry out all those computations, and you have to do them in near real time for online prediction. So this is Jeff Dean, who leads Cloud AI. He leads AI at Google. And he did this back-of-the-envelope calculation in 2014. He says, everybody speaks into their Android phones for 3 minutes. It's going to basically use up all available compute resources. Not available compute resources at Google. Available compute resources in the entire world. But we're still speaking into our phones now. So what happened? What happened was, right, that compute got better. Right? Compute got better. How does compute get better? Typically, Moore's law, right? Everyone is aware of what Moore's law is? What is Moore's law? This idea that every 18 months or so, compute power doubles. Yes? Well, Moore's law hasn't applied for the last 6 or 7 years. Okay, so that green line is when Moore's law was very popular. All the magazines are full of it. Okay? By the blue line, which is 2005 onwards, it's starting to slow down. And by 2010, it's plateaued. So the last 8, 9 years, Moore's law hasn't applied at all. So how do we get the kind of compute power that we need? It turns out that now the solution is to build chips that use less power. So if you build a chip that uses less power, that is the only way you're going to get the kind of performance that you need. And the way you get a chip that uses less power is to build an application-specific chip, or an ASIC. And that's what TPUs are. So TPUs are chips where we've thrown out everything else that we don't need and kept only the operations that you need for machine learning. And that way you can pack more compute power onto a chip. Okay? So these are ASICs focused on machine learning. We're on the 3rd version of those. And these essentially provide you massive compute power. Okay? The other bit about TPUs is that you have to distribute it. Okay? Normally, right, once your data sets get large, once your models get large, one GPU is not going to be enough. You need 10 GPUs or 40 GPUs or 100 GPUs. But there's a rule in distributed programming, which is that just because you add a second chip or a second CPU doesn't mean you get twice the performance. Right? If you have something that finishes in 10 minutes and you add a second chip, it's not going to finish in 5 minutes. It's probably going to take like 7 minutes. Why? Because of network overhead. Right? These machines need to communicate with each other, and that slows things down. With the TPU, though, when we designed it for distribution, so the scaling is actually linear. So as you increase the number of cores, the amount of images that you're processing or the amount of text that you're processing also increases linearly. And the reason, we'll get into it when we get into the design of a TPU, but that's one of our design goals, is to make sure that you can distribute the model across more TPUs than you need. So put those two things together, the fact that a TPU uses less power, okay, so it is faster by itself, but also that you can combine a lot of TPUs and not lose performance, and you basically get a TPU that can, a TPU pod, which can be about 200 times faster than an individual GPU and cost less. Right? The costing less is also important. Okay, so you get better performance for less of a cost. So how does this work? Why is it faster? Why does it work better? Okay? So a cloud TPU board looks like this. You basically have a host VM, okay? A machine. It's just like a GPU. You have a machine, and attached to it is a GPU. It's very similar. You have a machine, and attached to it is a TPU board. And in this case, this TPU board contains 8 TPU cores. Okay? So you have each of those little things with the connectors on them. That's a core. And that's the thing that actually does the machine learning. What's the purpose of the virtual machine? The virtual machine needs to do all the other things that you need in ML. You need to read the data. Right? The GPU is not going to read the data. We have to feed the data to a GPU. It's the same thing here. The TPU is not a computational chip. It's not a general purpose chip. It can only do ML. So everything else has to happen on the VM, including, in some cases, things like evaluation, okay? Including things like pre-processing. So anything that doesn't fit into your TensorFlow graph has to get moved out and done on the VM, which means that if you want to get a model that's very fast, one of our first considerations is make sure that the majority of the work happens on the TPU and not on the attached CPU. Fair enough? Okay. Now, that machine itself can now be connected from a whole bunch of other machines that you need, including your Jupyter notebook running or your own machine or some other machine. So a TPU core consists of 2 pieces. It consists of a vector processing unit that processes vectors, arrays, and a matrix multiply unit, which is capable of doing only one operation, just one. It knows how to multiply 128 by 128 arrays. That's it. I mean, that's what we mean by we're building an ASIC chip, right? We build a chip that is super fast at doing this one little thing. And this one little thing is a 128 by 128 multiplication. So if you want your TPU to be fast, it would be really nice if you make your model do multiplications of 128 by 128. So your batch sizes, multiples of 128. Such that your everything else in your ML model becomes 128. The multiplication itself is not a regular float, it's called a BFloat. And what it does is it takes advantage of the fact that with machine learning, you basically need a lot of accuracy on the significant digits, not so much on the digits afterwards, right? So it reformats the floats to basically keep the accuracy where you want it. So it's not your IEEE float, it's a different kind of float. It's called a BFloat. Okay? So this is what a BFloat is, right? And typical float 16, okay, will have like 5 bits for the exponent and about 10 bits for the mantissa. Instead, a BFloat 16 will use 8 of those bits for the exponent. Basically, we want to make sure that the order of magnitude is correct. And we're not so worried about the precision of the number itself. So we're using a BFloat 16 rather than a float 16. A float 32 would, of course, be double. We're not going to go to a double. We're going to use floats. Fair enough? So in your model, you're going to be using mostly floats. And the intent in the version 1 of it, we had to deal with all of these conversions. In version 2 with Keras, underlying the framework handles it for us. Okay, so that's what makes programming with TPUs this time around a little bit easier. We don't have to deal with it, we just have to know it's happening. So it is a lower precision arithmetic that's happening, but we don't have to worry about it. It's happening underneath the scenes. Okay. The second bit is it's super fast because it's a matrix multiplication. Okay? And this is basically showing you how that matrix multiplication actually works. Okay? It's basically taking advantage of a systolic array where once you get this 128 array, it's basically doing all of these multiplications in parallel, okay, with a whole bunch of different options. And then the last bit that I talked about, which is that one chip is not by itself, it's part of a pod, and you can basically take all of the things on that one board, and you can add more boards to it, and they all have that really high-speed toroidal mesh to make sure that the network, it's just as fast to talk between 2 TPUs that are on different boards as it is to talk to 2 cores that are on the same board. It's only when you leave the pod that you start running into distribution limits. So instead of thinking of 1 GPU now, we can say we can go up to, right, an entire pod and still get the same performance. And yeah, so this is basically showing you that interconnect. Okay? And the whole idea when you do ML is that you're basically doing this computation, you're computing a gradient descent, and that gradient descent is basically getting averaged on this entire toroidal mesh. And the gradients are getting computed so that by the time it leaves the pod, all of these guys have collaborated and computed their gradient before it moves on to the next step. Okay? So we've had different versions of TPUs. TPU version 2 is 8 cores, it's generally available. It's got about 512 cores. The TPU V3 is even bigger, right? And it has more chips, and it's about 8 times faster. So overall, it adds up to a lot more performance than what a V1 or V2 gave you. So that's a TPU. It works, okay, faster, basically because of that faster networking, and it works faster because it does that one operation, 128 by 128 multiplication of BFloats. Okay? So how do you develop with a TPU? To develop with the TPU, right, you need to do a few things. First thing is Okay? You need to basically make sure that your model doesn't require isolated running. It has to be able to be replicated so you can do things in parallel. Second bit is that your model should not have host latency. That is huge. Okay? What do you mean by host latency? By the time a TPU has done doing a computation, the next bit of data needs to be there. Okay? It should not sit around waiting for an I/O pipeline. So your data reads, you have to make sure that they're super fast. So I'll give you suggestions of how you make your data pipeline super fast. But if your data pipeline is slow, a TPU is not going to help because you're underutilizing your TPU. So again, this is the same thing as with the GPU. So best practices on using a GPU definitely carry over when you're using a TPU, except that a TPU is about 20 times faster. So in the GPU, you could get away with not doing best practice. With a TPU, it will stare you in the face, right? That you're not filling up all of the computation. The third bit is interesting. Remember that it does matrix multiplication, but not just any matrices, 128 by 128, which means that the shapes have to be restricted to that size. Okay? And so how do you restrict something to that size? Well, you use multiples of 128 whenever you can, but every once in a while you will come up with something that doesn't come up to a 128, and at that point you pad it to make it 128, run it through your network, and then remove the padding afterwards. And again, this was something in version 1 we forced people to do themselves. Right? In version 2 with Keras, we do it for you, right? So but it's happening underneath. Okay? The tensor padding and the static shape restriction. So in order to develop with it, the enterprise way, the easiest way, is to essentially use what are called the deep learning VMs on Google Cloud. So this is where you can go to the GCP console and you can create a notebook instance. And that notebook instance can have a TPU attached to it. Okay? So that deep learning VM, that's what is running the notebook instance, and it'll have a TPU attached to it, and then you can basically go ahead and run your Jupyter notebook just as it is. Today, Kaggle kernels doesn't support TPUs, but I believe it's in the roadmap. Right? Addison says, yeah, sure. Right, but it'll come, right? Basically, because all of the Google Notebook products ultimately will support them. So today, in our workshop, we'll use either Colab or we'll use Jupyter on a deep learning VM. Okay. So the second bit is how do you develop with it? You're going to be writing a Keras model. So the Keras model, okay, has to basically use TF data. Okay, TF data is basically the TensorFlow 2.0 of reading data. But it works in TensorFlow 1.11 onwards, right? So if you're using a stable version of TensorFlow, you should be using TF data. And the idea behind the TF data is that you basically use your TF data input function with a few things, right? Number one, you make sure that you're reading things in parallel. Okay? So in this case, how many threads are going to be reading the data? 32 threads. So when you write your input function, you're basically saying that I want 32 threads to read the data. I would like you to cache the data. So if you already have it in memory, just supply it. Don't go back and read the data. And you basically batch it and drop the remainder. So remember we talked about it has to be multiples of 128. What we're now saying is, suppose you have a data set that is 1,000 lines, and 1,000 is not a multiple of 128, go ahead and read 996 or whatever it is, and throw away the remainder 4. So we won't train on those 4 things that go beyond that 128. Isn't that a problem, throwing away data? Well, remember what happens during training. How many times do you read the data? Number of epochs. Everyone okay with that? You read it num epochs times. In reality, you're probably reading it 30 times, 40 times, 50 times. If you're reading it 50 times, 49 times you're reading all of the data, and at the 50th time, you're throwing away the remainder. It's a big deal, right? You're throwing away that remainder 4 on that very last epoch. Cool? Yes.
If you have like multiple TPUs or TPUs on the same machine, do you, for example, like set batch size times 4 or you know?
That is a great point. This batch size is a per core batch size. Okay, so this is a per core batch size, and then internally, like every one of those like cores will get their own pipeline with these things being fed. And the way you do that is by making sure that your num parallel calls is a multiple of the number of cores that you have. If you have like 6 cores, make sure that you have the parallelization of at least like 30, 32, 34, whatever. That way, any thread that has data will be able to feed it in. And then you do that last bit. You say, go ahead and prefetch the data. So every thread, right, while the TPU is computing, it's basically prefetching the data on the background, filling it, keeping it ready. As soon as it's done, it pushes the next bit in. Okay? So you want to do all of these things. You want to parallelize the read. You want to cache things. You want to basically batch it in a multiple of 128 if possible, okay? Dropping the remainder, and finally, prefetch. Okay, and that 1 means it's an auto-tune. So size of the prefetch is auto-tuned. Yes?
So it's not clear from the code to me which part is run by the virtual machine and which part is actually run by the TPU.
That's a great question. Which part of this code is run by the VM and which is run by the TPU? All of the input pipeline is run by the VM attached to the TPU.
So we put the batch size custom for the architecture
Right.
so the VM will then expand that to however many TPUs there is.
Correct. The batch size is the per core TPU, and then we're running this thing in parallel. And so this is basically going to, essentially a VM is going to feed the TPU with as many TPU cores as there are, and give each of them that batch size one at a time. And it is going to basically read it, prefetch it, it's going to prepare it, and have it ready for the next bit. Okay. Cool? Okay. The model itself is identical. Okay, so this is my Keras model, and basically I can use a sequential model, I can use any other type of model, I can do a functional model. I create my model, and then I say model.compile. That works exactly the same. Okay, so there's no difference as far as the model itself is concerned. Okay. With the one difference that you then take your model and you call this Keras to TPU model. So after you've created your Keras model and you've compiled it, you take that model and you basically call Keras to TPU, passing in a distribution strategy. So distribution strategy, again, is new in TensorFlow 2.0. This is the way you do it. And for GPUs, typically you use mirror strategy. And for TPUs, you use TPU distribution strategy. So, and again, this works in TensorFlow 1.11. Okay, so you don't have to wait for 2.0 to use it. So you basically do Keras to TPU model, passing in the Keras model, passing in this TPU distribution strategy, and that TPU distribution strategy is essentially constructed using a TPU. And you want to basically create the TPU by calling the TPU cluster resolver. Currently it's tf.contrib, in 2.0 it will change. Okay, but for now, in 1.12, 1.11, etc., it's tf.contrib, TPU cluster resolver. If you have only one TPU attached, you can leave out the TPU name and it will find that TPU. Right? You need to pass in a TPU if you have 2 or more TPUs attached to your machine. But otherwise, you can leave out the TPU. You get your TPU model, and then you say TPU model.fit, passing in the training data set, passing in the validation data set. Currently, there is a difference. Normally, when you do Keras model.fit, you pass in that data set itself. When you call it TPU model.fit, you pass in a function that returns the data set. Okay, so normally, in Keras, you would just give it the data set. In the TPU, you would be TPU model.fit, you would give it a function that returns the data set, because that VM has to call this function when it needs to. Okay, so you're not going to give it a data set. You're going to say, here is the function that gives you back your data set. But other than that, it is the same Keras model, same input function, same everything else. The big difference is that you want to make sure that your I/O pipeline is very efficient. But writing an efficient pipeline, hopefully, is going to help you regardless of where you are, right? Whether you're writing a CPU or a GPU or a TPU model, you do want to write an efficient pipeline, so you might as well do it. And if you do it, then this is essentially the only thing that you have to do, Keras TPU model. Cool? Okay. So here's a basically quick demo. So this is how you create a deep learning VM with a TPU attached. So it has, now I'm just creating a deep learning VM with a particular machine type. And the key thing is that startup script, which basically says, export the TPU name to be this attached TPU. And that TPU itself is gcloud computes TPU create TPU name. So 2 gcloud commands, one to create the thing that runs a Jupyter notebook, and one that creates the thing to run the TPU. Okay, so you have your 2 things, and then you can basically go into your notebooks, and there it is. That's my TPU that I've created. There's a link that says Open Jupyter Lab, and at this point, I'm now in Jupyter. And in this case, I'm opened a terminal, I'm git cloning, I'm opening up a notebook, and I'm going to basically be running this notebook. And this particular notebook, right, you'll get to do this at the end of this when we try this out. This is one of your choices. This is basically going to be an image model that we wrote, a little convolutional network to classify flowers. And this one is basically going ahead and getting the TPU. There is a TPU cluster resolver. In this case, there's only one TPU, so I'm not passing in a TPU name. Once I get my TPU, it figures out what that TPU is. And notice now that if it's a TPU, my batch size is 128. Otherwise, on a GPU, it is 32. See? That's one change that I'm making. Right? I'm using larger batch sizes on a TPU. And then another thing that I'm doing here to make things fast is that I'm storing my image data as TensorFlow records. That is the fastest way to read data into TensorFlow. Again, you want to optimize your I/O pipeline. So you do that by writing it out as TensorFlow records in some pre-processing step. So now I have my TensorFlow records. I can train my Keras model. All that part is pretty much the same. It basically classifies the model. And then what I'll do next is that I'll stop the TPU, and I'll start off a GPU instead. And then I'll basically run the same thing. And I won't go through this. Okay? But essentially, the same notebook runs on both TPUs and GPUs, with that one. The only differences being the things that I have if TPU, batch size is 128, and if TPU, do TPU model.fit, otherwise do Keras model.fit. Okay? So that's pretty much the only changes. So you can use that as an example for pretty much anything else that you write. Okay? So if you're basically writing any kind of image model that you need to write. So that is if you're writing something from scratch. But usually, you want to basically say, do I have to write it from scratch? Can I not use ResNet? Can I not use RetinaNet? Right? Something that is well proven in the whole research community, and we want to take that as a starting point for pretty much any models that you write. So we have those models already adapted for the TPU, and those are available. So we have a whole bunch of reference models that are already available that run much faster on a TPU. So if you're thinking of image recognition, you're thinking of object detection, right? Object detection is a RetinaNet model. You can use ResNet of different sizes for image recognition. If you want to run something on a low resolution thing like TensorFlow Lite, then think about MobileNet or SqueezeNet. If you want to do machine translation, right? Think about tensor to tensor for language modeling, sentiment analysis, etc. For speech recognition, we have an ASR. Actually, on the machine translation, we also have BERT. It's not listed on this slide. But you have them. There are more models coming, and all of them are in that repository. It's a TensorFlow repository, github.com/tensorflow/TPU. So all of the code is available. Take those and use that as a starting point whenever you're trying to solve one of these problems. Yes?
Those one classically trained on 128 times 128, and you retrained all those
Oh, okay. That's a great question, right? The image sizes can be different. The first thing, right, which is the batch size, is what has to be 128. Okay, so the next bit, so again, remember we do these things automatically. So if you have an image of size 223, right, what it's going to basically do is that it's going to basically say, okay, this is 128 images, and I'm going to take my 223, and I'm going to basically do it in two folds. I'm going to do the 128 first, and I'm going to take the remainder, whatever that is, 72 plus 23, and I'm going to then pad them up with zeros, and I'll go ahead and do the computation and remove the padding. All that is all automatic. Okay. The only thing that you have to remember, right, is that your batch size, multiple of 128. Don't try a batch size of 12. Okay. So that's pretty much it. Okay. And that's going to be the same thing if you have text models. Your words can be anything. Your sentences can be 10 words, 12 words, 15 words, whatever your document length is. But make sure that the number of documents in your batch is a multiple of 128. Does it make sense to everyone? Your images can be any size, not a problem. Yes, all the filters and everything, any size that you want. So you can have your convolutional filter that is 12 by 12, and that's not a problem. Okay? The key idea is the thing that you're feeding in, right, is that first dimension has to be a multiple of 128. And everything else we will handle. Right. It does that for the input layers. But then after that, all your multiplications, if you actually look at the math, it's a batch size that comes in each time. Okay, so it doesn't, after that, it's fine. Right? Just make sure that your batch size is a multiple of 128, and everything will carry through the rest of the computation. Cool. Okay. So if you want, for example, ResNet, so this is a measurement, right? So ResNet 50 on a TPU V2 pod, 77,000 images per second. Again, that's the code directly from the repository. It trains ResNet in 30 minutes on ImageNet, which is, of course, millions of images, and you basically get a 93% accuracy. So you can train, we like to call it the fastest ResNet in the West, kind of. So you basically get a really fast ResNet training model, and that's directly off the TPU Models official ResNet. Okay. For production, right? Once you have that, you can basically use ML Engine. You can use other things to any of the typical cloud tools to go ahead and do your prediction. For serving also, you can use any of the typical cloud tools. I won't go through into those. So the second bit, now if you were going to look at how to basically train and deploy ResNet, there is a Codelab that basically walks you through the process of training a ResNet model on your own data, in this case, Flowers data, and basically training it on a TPU and getting the result back. So there's the link for that. Okay. The next, right? So that's image models. Text models, state-of-the-art text model, use tensor to tensor. So tensor to tensor is an open source framework that helps you with a variety of different text summarization, question answering, and all of these things. Now we have BERT as well, but tensor to tensor is much more fully featured. It does a lot more things. And so here's an example, and this is another one that you get to try. So I want to basically create a model that completes lines of poetry, right? So if the model is going to get trained on actual poetry. So if you have a line that says, I wandered lonely as a cloud, you say the answer is that floats on high over vales and hills. So you go back, you go and find a whole bunch of corpus of English poetry and train it so that if you give it one line, right, that's the next line of poetry. And then after it's all trained, you hopefully give it some random line of text, and the model basically comes back and gives you another line that hopefully is poetic. So the way you do that, and so this is now a custom model, right? So I'm saying I'm going to create a poetry line problem, which is a text-to-text problem. My input is a line of text. My output is a line of text. So in tensor to tensor, if you inherit from image to text problem, you have a captioning. An image in, text out, it does captioning. Okay? Cool? And you do text to text, you get text. If you do image to image, you basically have a GAN. Okay? So you basically have this very powerful way of dealing with different kinds of tasks. So if you haven't played with tensor to tensor before, I encourage you to go try it out. It helps you in a variety of different deep learning things. In this case, I'm doing text to text. I'm basically saying, go find 4,096 words to form your vocabulary. And then each of my inputs, the previous line is my input, and the next line of the poem is the target, is what it's basically going to get trained on. And then I basically run a command line tool that's called data gen, tensor to tensor data gen, passing in my code, the code on the previous slide, with the data directory, saying go ahead and create a bunch of data. And then you can basically also customize it. The normal model is built for translating German to English. It's humongous. Our poetry data set isn't as large. So I basically go ahead and make the model smaller by reducing the number of hidden layers, by using fewer words to go ahead and do the attention, et cetera. So you can customize the model. And then once you do that, you just train the model. And when you train the model, you say T2T trainer. And you can basically specify CloudML engine worker GPU equals 1 to train on a GPU, or use TPU equals true to basically train on a TPU. Okay? So it's you basically change the command to train on a GPU or a TPU. So with that, enough of me talking. Go ahead and try it out now. Okay? So either try it using Collab, which is free. So go to collab.research.google.com and open one of the notebooks listed in step 4 or step 5. So git clone this repository from Collab, okay, and try out Keras Flowers TPU, that's the image model, or sequence poetry.ipython notebook, that's a text-to-text poetry prediction model. So do one of these two things. So go ahead and use Collab, it's free. You should be able to basically get it. Then once you open the notebook, do edit notebook settings, select a TPU from the hardware accelerator, and start running through the notebook piece by piece. Read what is going on. If you have questions, let's raise your hand and I'll walk by and try to answer it. If later on you want to basically, the thing about a Collab TPU is that it's going to go away after a few minutes, right? So it's okay for a session like this, but if you want to use it at work, you want to use it something that you totally own, then what you want to do is you want to use a deep learning VM, get your own TPU, and I have the steps on the right-hand side. This is when you get back to work or wherever, and you want to do it yourself. For here, use the one on the left, the free stuff.